Hi, welcome back to the breadboard and another TI Tuesday. About 2 years ago I did my first review of a TI product for Element 14. It was part of a road test, and what this was a battery booster pack. So it had a lithium-ion battery charging circuit, and some buck boost converters along with a gas gauge. And at that time I found a few, let's say, design issues that I fed back to Element 14 and included in my review, and I'll provide a link to it in the post for this. And shortly after the review was done, maybe I don't know how many months afterwards, the booster packs kind of stopped being made. So Element 14 wasn't making them anymore and providing them, and I just felt that it was a bit of a shame that they seemed to have disappeared, and nobody really could tell me why and anything like that. Anyway, now, just recently, Texas Instruments has released a version 2 of these booster packs. So now you can get a lithium-ion booster pack that will provide your low power projects, or high powered ones, with plus 5 volts and plus 3.3 volts to run them from hours to days to weeks, depending on how you configure them. So what I want to do with this TI Tuesday is have a look at the new booster pack and maybe make some comparisons in its design to the old one and give it a quick go. One of the things I'm going to look out for in this review is to see if the new design has fixed any of those issues and whether any of the older features are still there. So let's go to the bench and have a look. So what we have here is the original BOOSTXL battery pack that Element 14 and Texas Instruments did together, and this on the left is the new Mark II fuel tank booster pack that is from Texas Instruments. And the first and obvious thing that you can see here, let me just zoom in a little bit, is that the original one had the sockets and the circuitry on the same side, and the new one has the pins and the circuitry on the same side. Now if you look closer at the designations, this left one is J1 and this right one is J1 over here. So what's changed with the new design is they basically flipped the booster pack upside down as far as the load of the circuitry is concerned. So when you put them this way, they're both electrically the same on their pin outs. They haven't made any mistakes or anything like that with the pins instead of socket. So this is correctly configured as far as the pins are concerned. It's just loaded on the other side of the board. Now, taking a little bit of a comparison here, and we will have a look at the schematics. I'll put them up as we go through the video, and I'll do a separate section to actually do a comparison of them. What we have is the charging chip, which is up here, and it's the same on here. So we have a newer generation of the charging chip. So the original booster pack used the BQ24210 lithium-ion battery solar charger chip, which could provide charging current into the LIPO battery, and as the name implies, it also had some abilities to be run from a solar array, or at least a solar battery, a solar cell anyway. The new battery booster pack is using the 24250 polymer charger, which is obviously a newer generation of it, and we'll look at the specs a little bit partway through the video. The other significant chip, which is to do with the operation of the board, is actually a gas gauge chip, which in the original booster pack was the 27510G3 system side impedance track fuel gauge with direct battery connection. And again, we'll look at quickly look at the specifications for that. The new booster pack is using the 27410 fuel gas gauge, and again, there were some things that I noted on the original one with potentially its settings and things that didn't seem to work right, and we'll have a look at the specs in here. But for this video, I'm not going to go into a thorough in-depth testing of the new booster pack. We just want to have a look at it and everything else. I will do a follow-on video where we will actually give it a full charge discharge kind of load test and things to see how well it does. So there's a couple of new chips that have been included on here. As I said, one is for charging the battery, and one is for actually monitoring the battery condition, so it can tell you how much charge is left in the battery and things like that, and how long it'll take to finish charging it, or when it's, it'll even estimate how long you can run the battery for before you run out of juice, because it actually keeps track of the volts and the current feeding in and out of the battery between its programmed supply ranges. The other chips, based on what I'm looking at in the circuit diagrams, and I'll put those up and we'll have a look at them again in a minute, is the buck and boost converters. And these are actually using the exact same chips as what was used on the original design, so there's no changes there. And one of the issues that I had with that one was that the default jumpers for the mode of operation caused these buck boost regulators to consume a lot more current than power than what you would really want it to do for low powered operations, causing the battery to be discharged in a matter of days, even without anything being connected to it. And you really want to have your primary load being the prime consumer of the battery, not the actual battery control circuitry itself. So it'll be interesting when we look at the schematics to see whether they've moved the default position of those jumpers. Now, if they haven't, it's a well-documented fix that I did actually mention in my previous videos, and which I will show you again on the schematics. So if you do have an issue where you're consuming too much power, or you want to make the battery last a lot longer, and I'm talking about going from days to weeks, then a simple movement of a couple of surface mount resistors will fix that problem for you. Some obvious other additions on this board is that the new one has a switch for disconnecting the battery when you don't need to be using the board, which is really nice, because these little connectors that are on here tend to they're a little bit finicky pulling them in and out, and I've always been concerned if you do it too many times that you'll either damage the connection to the PCB or pull a wire out. So having the switch added is a really nice touch. Now, the other thing that you can see here is over on the original board, the Mark I, let's call it, there are two diodes that were actually put in series with the output of the buck boost converters and to the pins of the XL headers. And one of the things I highlighted back then was that even if these were Schottky diodes, you're still going to lose 200 or 300 millivolts of drop across those diodes when you've got the board being used to power a Launchpad or something. And that was a concern to me, because on 3.3 volts, if you're dropping 200 millivolts, now you're only running at 3.1 volts, which is really not a lot of good if you're relying on having the proper voltages for some chips that may be connected to this. So I've noticed in the new board, and I just had a quick look at the schematics, there are no diodes now in that output of the two buck boost regulators, which is nice. So that is one improvement that I've seen already. The other one that I've seen on here too is that there is a battery low LED on the original design, and there is no such battery low LED on the new design. Now, that's a good thing as far as I'm concerned, because one of the issues that came to mind with the original design was that when the battery got low, it put an LED on, which actually increased the load on the battery, which is kind of defeats the object of the exercise, if you know what I mean. Whereas the new board doesn't have it. Now, the gas gauge and the LIPO charger still has pins coming out to the XL connectors, so that your microcontroller can monitor whether the battery is low and things like that through a GPIO pin. But also the gas gauge in both cases is communicatable via an I2C interface. And that's the other thing I want to try and see, is if the I2C on here works a little better than what it did in the original design. I had some issues where I had to request data twice in order to get valid data out of it, and a few other things. So there was a couple of quirky things with the I2C bus. So again, we'll have a look to see if that's functioning. And So what else is included with this board? Well, you get a 3.7 volt, 1200 milliampere hour lithium battery, and that has protection circuitry built onto it by the look of the battery pack, because you can see, I have to see, it looks like there is some circuitry in here as well. I'm not going to pull the tape off right now, but it looks like it's got a little protection PCB on the batteries too, which is nice to see. They just plug right into here. There is one less jumper over here, so we'll have a look at what this jumper that's been left now is connected to see what it does. And I think that's pretty much the only two differences. I mean, the board layout is slightly different, and if I put this one over the top of this one, you can see the new board is slightly wider, and it is about the same length. So aside from what I've already mentioned, these boards are pretty much the same. They certainly are designed to provide the same functionality. So that's a little walk through the two different boards, and this was the original one, as I said, from Element 14 that was discontinued, and I've been eking life out of these things for a few years now, because I have a few of them and I couldn't get any replacements. So it's actually nice now that TI have come out with the new one, and that they've been kind enough to send me a couple of them so that I can do a review on them and have a play with them with some of the launch pads and booster packs to see how well they perform. So let's go now to a schematic and see if we can have a look at what electrical differences there are. So we'll bring up the data sheets and have a look. And then once we've done that, we'll come back to the bench and I'll power this thing up, put it on a launch pad, and see if we can run some of the test sketches that will be available for it. So what we have here is the schematics of the new booster pack. I also have the schematics of the old one right here. So if we just look at, first of all, the buck boost regulators, you can see here that we're using the TPS 63001 and the TPS 63002. One of them generates 5 volts, one of them generates 3.3 volts, and you can see these Schottky diodes that have been put in series with them to the outputs. Aside from that change, if you look here, you've got the TPS 63001 and 002 again. The difference is that they've replaced the diodes pretty much with a 0 ohm resistor. So if you go back here, capacitor, diode, then output, this diode has been replaced with basically a short from a schematic perspective. So that's an improvement. Now you're actually getting the true voltages out because the set points for these regulators is built into them. The other change that we have is there's no jumper now between the outputs and the pins on the connector. The gas gauge is on the new board is the 27441, and the old it was the 27510. And the actual LiPo charger on the right hand side here, this is the new board design, is using the 24250. And the old design was using the 24210. You can see here that this one only has 1, 2, 3, 4, 5, 6, 7, 10 pins on it. The new one has a lot more pins. It's got the I2C interface on the charger. The old one didn't have any I2C interface. It just did its job, I believe. Yeah, there were no communications to the microcomputer for it, whereas the gas gauge had the I2C interface. On the new Mark II design, both the gas gauge and the actual charger have the ability to be controlled from the Launchpad microprocessors if you have one connected. There is the option for a thermistor, and I know that the features talks about being able to measure the temperature of the battery. But looking at the board and the design here, the thermistor itself is not populated. But I don't see why you couldn't plug in one of your own if you wanted to. The other parts that I can see here that might be different to the other previous design on the charger, you've got the charge light, you've got that's the only light that's actually connected to the charger, and I think that's the same here. We'll have an LED here connected to the charger. And if you look at the gas gauge on the previous design, there was an LED also connected to the battery low on the old design. And here you can see clearly that there is not one. There's your battery low output. Now that battery low, by the way, is connected to both the buck boost regulator for 3.3 and 5 volt rail. So when that battery low signal activates, it will shut off the buck boost converters. Now this is a good thing if the voltage threshold where that activates is set correctly. In the original design, I found that the battery was still well into the 3 volt range, and that signal, which is battery low here on this case, went low and actually turned off these regulators very much prematurely, and left a lot of charge left in the LiPo battery. So it'll be interesting to see once we get to testing this as to where the low threshold is for this to cut off at. The other changes here, really, there's none extra ones. I think there's more pins that are connecting to the XL interfaces. As you can see here, there's quite a few. The bin, which is the battery connected indicator, is actually just connected to a jumper, I believe, on here. It's not connected to the bin output. So if you connect the jumper, then you will have the output from here running. Now by default this is not connected, so the pin is going to be and that's pretty much it. The battery specifications is there we go, battery specifications. So 1200 milliampere hour typical, 3.7 volt nominal voltage, 4.2 volt charging, plus maximum charge voltage. So that's what you would charge it at, plus or minus 0.05, so plus or minus 50 millivolts. Maximum charging current is 1100 milliamps, so 1.1 amps, so it's almost a 1C charge capability. This is the limit of the battery, not the charger. Maximum continuous discharge current 2.2 amps, so you can discharge at 2C but only charge at 1C basically. Discharge cutoff voltage is specified here at 2.75 volts, so we'll see where the low battery indicator actually cuts it off as. So this indicates the pins that are being used by the booster pack. The way that these work is the outer edges will show you the general use of the pins on these diagrams, and the pins that are marked right against these connectors are the ones that are actually being used. So we can see here that the I2C interface is connected, 3 volts is connected, 5 volts ground, the battery indicator, an interrupt, charge indicator, and a couple of enable lines and a chip enable all seem to be coming out to the booster pack. So if we go back to the schematics, the CE, whether that's just to talk to it or not, I'm not sure. We'd have to look at the specifications for the LiPo charger, and I think we may do that on a separate video. And you've got a couple of EN1, EN2 lines, and then your data and your interrupt. The interrupt is probably to let the microcontroller know when it's charged or if there's any abnormal conditions occurring. Now this LiPo charger as well also has a SIS output, which normally would be used to drive your microcontroller. It's actually a regulated voltage output from the battery, but in our case it's not being used. In the case of this design, the two gas gauges, the two buck boost converters are actually connected directly to the battery pack continuously. So if these are not shut off by the gas gauge, then they would continue to drain the battery right down to the point of it running out of capacity completely, and that would damage the battery. So it's good that because of the way this is connected, that it will protect itself by using the gas gauge to shut it off. Now if you were using the SIS output, of course, then the LiPo charger itself would probably also provide a certain level of protection. And we will have a quick look at the data sheets, but as I said, to do a more thorough review, we will look at doing that in a separate video. So that's all of the I think basic things that we want to have a look at here. So let's now go and have a look at the board and put it onto a Launchpad and give some of the software a whirl. So before we disappear and start playing with the board, I just remembered that I said I would point out and have a look to see if they had changed the default operating mode of the two buck boost regulators. So here's the original design, and we had the PS sync being populated with a pull-up to the pack positive, which put it into a mode of operation that consumes more power but does provide a more stable output voltage. And so the PS syncs were both connected high in the original design. Looking at the new design, that is still the case here. But the difference is at least TI now acknowledge that functionality. If I just scroll up to, I believe, the design sheet, let me just find it. Here we go. The TPS 6302, and it's going to say the same thing for this 301 as well. 3001 is that they have a power save mode of operation that uses less quiescent current but provides a slightly less stable voltage rail. To enable this feature, the PS pin needs to be pulled low. This can be done by moving removing R18 and populating R17. Basically move the resistor that's in the R18 position and put it in the R17 position. And that on the original design was right here, where the 10K resistor could be put down, which would then pull the PS sync line low instead of having it high. And you do that on both of them, and you can make a significant difference to how long the battery will last, but at the cost of having a slightly less stable 5 volt and 3.3 volt supply rail. Now, in the testing I did originally, I didn't notice anything that would actually cause any untoward problems in my testing, but that doesn't mean to say that in your solution you might not have that. So that's just something to be aware of in the design, that the battery, the default behavior is that the battery will discharge in a few days. Now, if you're using this as a battery backup and you're normally going to be powering your Launchpad solution from a USB port or a wall charger or something like that, and this is providing a backup, then it's going to run it for a couple of days quite happily, and that would be just fine, even with the more stable configuration for the buck boost controllers. Anyway, I just wanted to make you aware of that so that you wouldn't be surprised as to why they were discharging quite quickly, even when they're not necessarily connected to a Launchpad. Now, the nice thing, of course, is that now they've also included the switches to allow you to easily disconnect the battery without having to unplug it as well. Okay, so as you can see on the picture here, I've connected up the battery booster Mark II to this MSP EXP 432P401R Launchpad, and I've loaded a sketch onto it that comes pre-compiled, so I've just run an executable. I won't take you through doing that. I've done it on a couple of the other previous videos. And I'm running it now on screen capture, as you can see here, monitoring the voltage. It's being sent out through a serial port about every second. And you can see here that it thinks it's fully charged because I had a different battery, and one of the batteries looked like it was completely flat, which is what's in here right now. But as you can see, the voltage is quite low. But it thinks it's full, so I'm going to leave it for a while to charge up the battery. Neither of these batteries are full, so I'm just going to let it run with one of them to charge it right up until the current cuts off, and that'll be when the voltage reaches 4.2 and the current will come down. But this is the demo piece of software that you're looking at here, where you can see that it's actually queried the gas gauge to get the design capacity of the battery, which is showing 1.3 ampere hours, and it's showing the remaining capacity of the battery at 13 milliampere hours, which is pretty much discharged, really, if you think about it. That's because the gas gauge really hasn't figured out what's happening with the battery yet. So what I need to do is charge it up and then let it discharge. Probably one complete cycle would then set this thing correctly. And you can see here already that the remaining capacity has crept up a bit because it is pumping a charge into the battery at about a quarter of its C rating, so 235 milliamps is what's going in. Now a little bit of that is probably also coming right back out again and feeding the launch pad, but probably not very much. So what I'm going to do is I'm going to leave this video as it is. We already know now that the resistors for the buck boost converters are set so that they're in the stable voltage mode. And if you want to change it so that the batteries last a long time, and I will do a separate video with this where I'll compare it with the old booster pack. I'll run them in parallel anyway to see if there's any differences in charging and discharging times and stuff like that. But I think what's important here is that you can see that it's measuring the voltage quite nicely. And if I actually take a multimeter and see if I can measure the voltage myself as well, if I can get to it, because it's on the bottom of the board. Okay, I've as you can see in the picture here, I've moved the battery booster to the top of the launch pad instead of underneath, because the pins are on both sides, pins and sockets, then it's easy enough to do that. So now what I will do is I'll measure the battery voltage, and I've got a multimeter here. I'll just move that into view, and we'll see what the battery voltage currently is. On the screen here you can see it is currently showing a voltage of, oh, it's disconnected, so let's just connect it. I'm just going to reset the charger. It's not, might take a while before it goes in. It's quicker just to unplug it and plug it in again. Alright, so we're charging at 212 milliamps. It's reading 3.50 volts. So if I put my meter across here, so I got 3.51 on the meter, 3.52, and I'm reading 3.52 on the battery monitor as well, so that's pretty close. 3.53 it's just flipped into, yep, that's what it's showing up there. So let me just grab a higher resolution meter so that we can maybe compare the readings more accurately. So I'm currently reading 3.562. So here is 3.565 now, and I'm reading 3.569, 3.57, 357, 357. So yeah, they're they're tracking fairly accurately. I'm not capturing the data currently from the fuel gauge. I'm just showing it on the screen here, as you can see. So we got 3579, and we've got 3577, 3578. So it's within sort of like 0.1, 0.2, or 0.3% ish of the multimeter. So that's pretty good. I'm quite happy with that. So I think what we can happily say here, just to close off this video, is that the new battery booster pack seems to be designed fairly well. I think my own personal preference is that I prefer to see the voltages output of the buck boost converter set to economy mode to increase the length of the battery, but I mean, I'm quite capable of moving those two resistors fairly easily. The battery is happily charging, and the buck boost system is performing as to expectation. So I will finish the video here and say, yep, I'm glad to see that TI have come out now with a new effectively a battery backup solution for the launch pads. And to be honest, you know, these little solutions will work with pretty much anything. You could even hook them up if you wanted to an Arduino or a Raspberry Pi. There's plenty of capacity to be able to drive them. Well, maybe not a Raspberry Pi, because these will only give out about 800 milliamps on the +3 and +5 rails, and that's not enough for a Raspberry Pi, but certainly for Arduinos and other small circuits that you may want to build, this is more than adequate to be able to provide a sort of a battery backup. Or if you were going to use an ESP8266 or something like that, it would certainly work for that. For the launch pads, obviously you can see right here that it's been working quite happily, slowly charging up. And anyway, I will do another video where we will completely look at the full charge discharge cycle, and I'll see if I can set it up with a separate sketch that we can log the data out to a graph, so that we can look at the profile, see if it gets the battery working properly, see when it cuts off. It's difficult to see when the battery voltage is going to cut off when it takes so long to discharge, and you know, I don't want to be having to sit here the whole time. So what I'm going to do is I will get it hooked up with a monitor so that we can actually capture all the data and see when it stops charging. Stops discharging. And we'll see what voltage that is. We already know, we've confirmed that the voltage measurement is accurate. And we'll also put on a logging multimeter. I've got my Keysight 34470A, which is 7.5 digit multimeter, and has all the trending capabilities and things. I'll fire up Keysight's bench view software or something like that, so that we can capture the data while we're monitoring from the text, and we'll actually capture the real data as well. We'll measure the voltage and the current. Anyway, I think that's it for now. I actually quite like that they've come out with this again. I'm very happy with what it seems to be performing like, and as I said, we will do some more testing to do some actual performance testing rather than just a here it is for a TI Tuesday. So I will see you next week. Bye.